Okay, well, welcome to my presentation. My name is Gorte. Beryl, the third author, and me are working in the geoscience and remote sensing department at the Delft University of Technology, and also in the middle, Andres, he's engineering, and he brought us to this project, in fact, because the full title is called Camera-Projector 3D scanning as such, but that will be what I will talk about how to do Camera-Projector 3D scanning. But in fact, it is Camera-Projector 3D scanning of a semi-submerged terrain in a flume. And what is a flume? Well, this is going to be the flume. It's a very big concrete structure that we are making in the hydraulic engineering department of our university. It's like 50 meters long and 5-6 meters wide. And they will fill it with sand, and they will have water flowing over it. And then they hope that this water will make a kind of channel in this sand. And they don't know yet what this channel will look like. At least they have models to do the same thing, but they want to see the models are incorrect. So perhaps this channel will become quite wide or quite deep, or it will start to meander. And well, we'll see, but meanwhile they want to monitor that, so all the time we want to make PTMs of this sand. And part of it will be under the water, and that's in fact the most interesting part. So that's why they start to wonder how to do that. Well, they can do that with line scanners. They do have line scanners, which you have to move around, go back and forth all the time, make profiles, I don't know what, but we're asking, cannot we make a DTM at once all the time? For example, with a laser scanner, well, laser scanner, if it's an infrared one, then the water absorbs the radiation and it doesn't work. So then it would have to be a green one, but this again very expensive, and they found a few papers on doing that with photogrammetry. So that's why they came to us. Can you do that with stereo photogrammetry? So we start to draw on the blackboard, on the whiteboard. Well, there's an ISPRS event, so everybody knows photogrammetry, but if you have two cameras, one left and one right, and to have oriented them nicely, you know the orientation parameters of both of them, and then from image coordinates of corresponding point in the left and right image, you can construct 3D. Yeah, that would be definitely an idea. The problem is, of course, how to find these correspondences, and the texture in such a flume might be a little bit older. So somebody got the idea to replace one of these cameras by a projector like this, such a beamer. So what you then get is the famous structured light photogrammetry. Yeah, then the correspondence problem becomes much easier because well, this projector starts to project known things on this landscape, and the camera records it, and what you have to do is find again those known things back in the camera image, and then you have a correspondence. So we thought that this might be a good idea, and we were hoping that this would eventually also work under the water. Although I will not say anything about underwater anymore because we didn't get to that point yet. So now it's just about getting 3D from a camera and a projector. This would be not a correct way to do it because if here there is water and the projector shines like this, then it will reflect straight into the camera and you get well, the same image that I am now, but such a white spot in the face. But anyhow, speaking about those patterns, what you can do is make this projector send out binary patterns like these in a sequence, and record them by the camera, and then interpret this black and white or these dark and light things as bit planes in a sequence of binary numbers. So So if you do this scheme, then what you can find very easily is the line number of the projector back in the camera image in the same way you can find the column number. And then you have perfect correspondences. If you want to do that a little bit more refined, then you use array encoding instead of binary encoding. I'll come back to that later. Here you see an example. So this is a very simple scene, and this would be the sequence of patterns that you project onto it, and every time you make an image. And if you want to do this at home, which I recommend, then I also recommend to use a parallel configuration. And this is in fact the topic of my story. So what you should do is you should put your camera and your projector quite close to each other and make them look in exactly the same direction. As opposed to a converging configuration where you have a projector here and a camera there. So what you get is a small base V, and you have two parallel optical axes. And well, the bad news then is, as you will realize immediately, that your depth resolution. So what happens if your disparity, the offset between the two images changes 1 pixel? What happens with your depth then? Well, it will go up with something that is proportional to the square of the depth. So that's already very bad. Further depth resolution will become not very nice. What we can do is compensate by making a larger base, so it will partially help, but this is what I'm not recommending. Or you can change the focal length, that will also help, but your image will become smaller, the congested zone will close. So both of these things don't make sense. You have to find out something else to get it right again. So the challenges are the depth resolution. The challenge in general is the depth of field. We want to be able to measure short distances, but also longer ones in the same scan. But especially these projectors, they don't have an adjustable diaphragm. So your depth of field will be the problem. So a challenge is to find sub-pixel correspondences, to measure the disparity with sub-pixel accuracy. That's what we want to do. That will be a way to get a better depth resolution. And of course you have to calibrate the whole thing nicely. The advantages of the parallel configuration will be that you don't have so much trouble with shadows and occlusions, you can convert them from the part. And a very nice advantage is that the pattern that you see on your image in the camera does not depend on the distance to the object. So if you have a camera and a projector and a wall there, you go with the camera and the projector towards that wall, then you see all the time the same distance between the stripes that the projector sends out. Another advantage is that you can make a mobile system out of the whole thing. Because if you take your camera and your projector and you nicely mount them to a piece of wood, then you can calibrate it once and then you can carry it around and scan different things and you get the construction completely automatically. Whereas if you have the camera here and the projector there, you want to go with it somewhere else, then you have to do the calibration again of a very massive thing. The calibration is required. You cannot really fix it completely parallel and completely the same height and things like that, so we have to still measure the orientation parameters, for example, gamma, the distance in the set, but also this angle. This is in fact not parallel enough. This was in the older days where I didn't realize that they had to be really small. This is a stupid angle that you have to calibrate for. This is because these beamers, when you put them on a table, then they don't shine like this, but like that. And anyhow, they don't produce a picture like this, but still like that. And that's actually a very nice example, except that it's upside down. But okay, all this can be solved. As can the calibration. What you have to do is, with your thing fixed on the shelf, make an image on the wall of the checkerboard, and measure some distances in the checkerboard, and measure the same points in your camera image. And after that, the calibration is done, and you can use it forever as long as you don't have to change the battery. Because you should buy this kind of camera and battery on the water. Okay, so coming back to this gray encoding thing, because of the depth of field, the highest frequency pattern by binary encoding, well, it's this one, 0, 1, 0, 1, 0, 1, 0, 1. It comes out like this. Very, very bad. The next one, or the ones over here that go 0, 1, 1, 0, 0, 1, 1, 0, 0, they're already much better. These are the two highest frequency patterns in the gray encoding, and this is the highest frequency pattern in the binary encoding. So that's an advantage of gray encoding. You don't have this very high frequency pattern. There are other advantages as well, but I will not go into them now. So that's why we use gray encoding in the first place. However, we do want sub-pixel disparity measurements. So what does that mean? Well, this is not so easy. Well, let me look at it a little bit. So this is the projectile pattern. So in fact, these are the projectile pixels, this size. This fine raster is my camera pattern, which is really much finer. This thing is 768 by 1024, and my next camera is 3000 by 4500. So for every 2 pixels from that thing, I have already 9 pixels in my camera. So these are the camera pixels. In the projector, this would be column 106, this would be column 107, this would be column 108. But these are not the numbers I'm looking for. I want to find that this pixel is column 106.0. And when I go a little bit down, then here I have that pixel column 106.1. And when I'm going from here to there, then I'm going gradually from 106.00 to 106.10. These are the subpixels that I want to make. To be able to do that, I exactly need my highest frequency pattern. I can do it in another one, but I lose a factor of 2 immediately. But I didn't like my highest frequency pattern. What do? I reconstruct it. My gray encoding requires to have the 2 at the top. See, here are 2 with the same frequency, but only one shifted with respect to each other. Here are the 2 that I come on the top here, and I make also the other 2. This one and this one. Again, 1 pixel shift. Now I multiply the other 2, also multiply third and fourth. These 2 results I add together, and I get this. This is synthetic highest frequency pattern. So I multiply the first 2, I multiply 3 and 4, I add it together. because under any normal assumption of blurring that happens because of the depth of field problem, for example, my bulky pattern of the projector will start to look like a sine wave. And if it's really a sine, I can apply this little formula, which exactly gives me a doubling of the frequency. If there are still blocks, by the way, then it works even better. And if it's somewhere in between sines and blocks, then it works also. So this is my synthetic pattern that I will use in my subpixel illumination. You see it again, the synthetic one, the original one. And now my question is, where am I at a certain pixel in my camera inside such a pattern? So what I see there is 9 values. 9 values. And I want to compare them with 9 values that I would have in a cosine function. What is the phase difference between this and that? This phase difference is my subpixel estimation. Okay. So what is the phase difference alpha between A and B, where A is cosine x plus alpha and B is cosine x, with unknown alpha? What I do is I convolute this with this. Means multiply these two, multiply these two, multiply these two, multiply these two, etc. And the result together. This is a cosine. I also make a sine, and I convolute this one with that sine. So I get two convolution results, C0 and C1. And then my alpha is the arc tangent of C1 divided by C0. And this works really well. As long as I know exactly the frequency. And that's why it's so important to have these camera and projectors exactly parallel. It works quite nicely. So these convolutions, in fact, I do them in images and I do them with kernels like that. But this one, 47, 25, minus 9, minus 38, is this one. The sine one, I don't use most of it. But then it works quite well. At the end of the story, skipping almost everything, but I hope you have the pictures still in your mind. I do get a 3D point cloud exactly from the 10 images that I showed you at the beginning with all these files. So the conclusion is you can build your own 3D camera as long as you use a parallel small baseline configuration, I would say. You do it like the Kinect does that. Kinect is the same, a base of 7.5 centimeters. They have much lower resolution cameras, but they do get subpixel determination of disparity. But if you use Nex 5 or Nex 7, beam like that, you get a much more accurate result. And I think you should do your subpixel evaluation by phase estimation, like I did with you. There are some future challenges that you might want to address. If you use a high definition video camera instead, then you lose some accuracy because you get 25 frames per second. If your software is fast enough, you can get 2 point clouds per second. 2 point clouds per second. This is already compete with Faro. And what, according to me, you also should try to do is segment them in real time. This is what I would like to do very much myself. In fact, if you see each other together in the next 3D indoor meeting, and I hope to show you some results. not scanning points, but you're scanning surfaces.